I am Mr. Tarou. Alright, we're going to start our examples of working with binomial proportions. And just as a footnote, sorry about the little correction I had to make on the last video. I wrote the mu of p is equal to p hat, had those backwards. Okay, we're going to use the same example that I used in my video about binomial counts or the binomial setting, just so you can see the close relationship between using binomial proportions and binomial counts. They're really exactly the same. Well, I can't really say that because the formulas are a touch different, the mean and standard deviation formulas, but other than that, it's still a binomial setting. You still have the same checks, the same check for normality, and we're going to be doing z-scores again for normal approximation. So, during the year's biggest holiday, it's estimated that 68% of people travel to see their family, and I just made these numbers up, by the way. If you survey 350 adults, or just people in general, what is the probability that, now I'm doing the 250 over 350 because I'm just showing you that I'm just taking the count value that I had in the original example, and I'm dividing it by 350 to convert it into percents. So, if you survey 350 people, what is the probability that 71.4 or 0.714% say that they travel, or 71.4% or 0.714, the proportion of people say that they travel to see family? Should probably just add that in there. Well, if you're going to do a normal approximation, you first have to make sure that it's a binomial setting. You have to make sure that it's actually normal, which now that I'm talking, I realize I forgot to put in here. So I'll add that in. And of course, you need the mean and the standard deviation. So the mean of p hat, the mean of our sampling distribution, should be the same as the population's mean, as long as it's unbiased, and certainly we do not want it to be biased. The standard deviation of p hat is the square root of p times 1 minus p over n. And while our sample proportion, or the question, is about 71% of the people saying yes, we're told that indeed 68% of the people travel to see their families. So it's going to be the 68% that we use in our z-score calculation. Remember, you do not use p hat ever in the standard deviation formula, and yes, unless you're doing specifically a confidence interval, and that's not what we're doing right here. So I have my 4 checks for a binomial setting. We have 2 outcomes of traveling or not. We have a set number of observations of 350. We need to have independence, and our statement there is generally going to be the SRS is assumed, because I didn't actually say I took an SRS of 350 people, and the population must always be greater than 10 times the sample size. That's what you need for independence, especially. And we need to have a constant probability of success, and we do if we're polling from a large population, and that actually truly is 68%. We have a constant probability of 68%. Now, if I'm going to do normal approximation, and all calculations with binomial proportions do involve z-score calculations, which we call normal approximation. Well, if you're going to do that, you need a normality check. So you need to make sure that 350 times the probability of success is greater than or equal to 10, and that n times 1 minus the probability of success is both greater than, both of those have to pass, they both have to be greater than or equal to 10, and indeed they are. So I've checked that I have a binomial setting. I've checked for normality. Didn't write it because I'm a little bit out of space here, but this is my normality check. And let's walk through some examples. I'm also going to show you a tie-in between working with binomial counts, those binomcdf and pdf commands, as well as, of course, hit the main purpose of this video, this example of working with binomial proportions is, again, how do you do a z-score calculation with this type of question? All right? Alrighty, so we're going to ask the question, or rephrase it from the previous screen. What is the probability that our sampling proportion exceeds 0.714? Yes. So I've drawn my bell curve. You always want to do that when you do z-score calculations, just to make sure that you let the person grading the test, that you understand what the population proportion is, where that goes, or the mean. your sample statistic, where that goes, which direction you're going to shade for the wording of the question, and then again, show all your work. I'm doing the tables, the hand calculations of z-scores, and the tables. So we have your standardized test statistic, that's what it reads on your formula sheet, or my z-score is equal to estimate minus parameter over the standard deviation of the estimate. We've already calculated that on the previous screen. We get a z-score of 1.36. Should that sound realistic or correct? Well, my statistic is to the right of the mean, and when we are to the right of the mean, the z-scores are positive, and let's just remind ourselves that the unit of measure for z-scores is numbers of standard deviation away from the mean. So 0.714 is 1.3 standard deviations, or 1.36 standard deviations to the right of the mean. At any rate, that gives a p-value of 0.087, or there is an 8.7% probability of having more than 71.4% of our samples say yes, they do travel to see family during the year's biggest holiday. Let's do an interval question where we want to find just the interval inside of a bell curve. I haven't done one of those for a while in a video. So what is the probability that between 66 and 71.4% of the sample says yes, they do travel to see family? Well, when you want the area of an interval in a bell curve, it is the area to the left of the large number, so the area to the left of 0.714 minus the area to the left of the small number. So I don't want this left tail area shaded, so I'm going to find that left area off the table and subtract it. So area to the left of the large minus the area to the left of the small value. So I picked the same number, so the z-score again is 1.36, and the area to the left of that value, 0.714, is 0.913, and then we're going to do a z-score calculation again for the small number, the number on the left. So z equals estimate minus parameter divided by standard deviation of the estimate. I'm using the words from your AP formula sheet just to get you used to that notation or that language again. We have a negative z-score because we are to the left of the mean. We're less than 1 standard deviation away from the mean, negative 0.8. And that left tail area that we pull out of our chart is 0.212. So from this 0.212 is the area to the left, this tail area that's not shaded because we're going to subtract it out. And when we do that subtraction, 0.91 minus 0.21 comes up to 0.701. I didn't write the summary statements because I wanted to get as many examples up as in this one video as I can. So there is a 70.1% probability that between 66 and 71.4% of my samples say yes, they travel to see family. And again, anytime you do a z-score calculation or you use normal approximation or use bell curves, that is a continuous random variable, even though the binomial setting is a discrete random variable. We're counting the number of people out of the 350 that say yes. And we have converted that into a decimal, but remember that when we studied binomial settings and binomial counts in the first place, that was a form of a discrete random variable. Well, anytime you use a z-score model, that's a mathematical model, that perfect bell curve, and that kind of puts us into the realm of a continuous random variable. So just for argument's sake, if I change this and I added a couple of equal signs into my inequalities, that would not change my answer from the normal approximation. So let's compare that fact where with this continuous model, when I change the inequalities, it does not change my numerical answer. It does need to match the wording of the question. How does that vary between what I've got down here in blue? Now, what I'm doing down here in blue is I'm showing you a couple of things. I'm reminding you about the binomcdf commands that you learned when we studied the binomial setting and binomial count setting. I'm also trying to tie in, this example from the previous video. And I remember from the previous video, I never did any examples about finding the interval between two numbers. So I've got the probability, well, first of all, I've done 66% times the sample size, which is a count of 231. So I'm kind of changing x from the percent of people that say yes to the number of people that say yes. And so 66% of our sample size of 350 is 231 people. 71.4% times 350 is almost, it was like 249.9 or something like that. So that's 250 people saying yes, they travel to see family during the biggest holiday of the year. So what is the probability that x, this now I've converted into a count to tie in with the binomial setting and counts and proportions again. What's the probability that x is between 231 and 250 without the inequality signs? Well, binomcdf, that's under second distribution of your calculator. Binomcdf, 350, 0.68, 249. Yes, because I want x to be less than 250, and the first count value less than 250 is 249, minus binomcdf, 350, 0.68, comma, 231, because I want to cut out, I want the count values that I want to be basically 232, that's greater than 231, I want it to be 232 up to 249. And it comes out to be 68%, a little bit lower than we got from the normal approximation. Now if I add in the equal signs and I want x to be in between 231 and 250 but including those borders, so I added the equal sign, well now my binomcdf statements for my calculator, I want 250 or lower, so I'm still finding the area to the left of the large number, but I'm using 250 now because of the equal sign. And I want x to be greater than or equal to 231. So I want 231 to be included in the answer. So 231 or greater cuts off 230 or less. So that's my last n value in my last binomial CDF statement. And when I subtract those with my calculator, I get 0.731. So you see how, like, if I don't include the equal signs, I'm a little bit below what I got from normal approximation. And if I do include the equal signs for this particular example, I'm a little bit above. So that's how that normal approximation works. It does give you a pretty close answer, but it is not exact. That's why it's called normal approximation. And change in the inequalities with a continuous random variable, it's important to follow the language of the question, but it does not affect the final probability. All right, one more screen or page of examples. Here we go. Here we go. Here we go. No, 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 no. Bam. All right. What are the effects of increasing the sample size? So I'm going to go back to my original example. That what is the probability that the sample proportion exceeds 0.714, the same probability as before, when we had a 8.7% chance of observing a statistic larger than 0.714. But now I'm going to make my sample size 1400. It's a much larger sample size. Well, let's do a little bit of algebra review. This sample is 4 times larger than the original 350, so the standard deviation should be reduced by a half. Here I've taken and added in a 4 where I'm multiplying the sample size by 4. I'm just using the standard deviation formula for binomial proportion. And we can take the square root of 4. So I'm pulling that 4 out and square rooting it. It is in the denominator where n is, and the square root of 4 becomes 2. So here's my original standard deviation formula with the 1/2 out front. So I'm going to increase the sample size by a multiple of 4, but that ultimately is going to decrease the standard deviation by 2, or by half, excuse me. So I'm recalculating the z-score calculation with, of course, a different sample size. I get a smaller standard deviation, which puts me, it gives me a z-score now of 2.7 standard deviations instead of the 1.36 that we had before. So it's still the same observed difference. But with the larger sample giving me a smaller standard deviation, I'm actually more standard deviations away from the mean. That is going to decrease the area in the tail. And now I can say that the probability of more than 71.4% of my sample saying yes, they travel to see family during the holidays, assuming that the original 68% was true, is 0.33%, a very, very tiny probability, which means that if I were to observe that 71% or higher proportion, then that's very strong evidence that the given information was false, because you always set up z-scores, and significant tests, that's language, I'm kind of getting ahead of myself a little bit with the language. You always do your significance test assuming the given information is true. Well, if it was true, and I did observe a sample proportion of 0.714, And that did give me supposedly a very, very small probability of occurring, but it was a very small probability of occurring if the given information was true. So this is what you would call a statistically significant event. The larger sample size reduced the standard deviation, making the observed difference much less likely, therefore a more statistically significant event. We're going to be talking about this concept a lot more in the following chapters, because it's the statistically significant events that allow you to question the truthfulness or the validity of the given information. If someone says something is true, you observe an outcome that was very, very unlikely. It could have been by chance, like people do in the lottery. But with statistics, we have to go with the odds. And if we observe an event that was very, very unlikely, we must conclude that there's evidence, or that it's showing that there's evidence that the given information was false. You know, if we assume that truly 68% of the people traveled, if we observe that 71%, and assuming that the 68% was true, given us this very, very tiny probability, would have us question, you know, is that 68% that you told me that travel, is that really accurate, or really maybe is it a little bit higher? All right? So that's it for now. We'll talk a lot more about this concept in the following chapters. I'm Mr. Tarou. Bye! Go do your homework.